Well, let me say a couple of things about the next homework first. Yes,
For discussing the newest homework, I want to ask something about one problem in the previous homework. You asked us in problem 2B to show that this assertion fails if R is not a domain.
can fail.
Can fail. So do you want us to explain why, or do you want us to give an explicit example?
Give an explicit example.
Okay.
So here's what's up next. So I haven't defined what an exact sequence is, but I will today. What it means to be exact is exact at some point if the image of this is equal to the kernel of this. So this first one is called 5 lemma. It is, so if you have the following commutative diagram of module homomorphism with exact rows. So what does it mean to be a commutative diagram? It means that if you start here and you apply functions, no matter what path you take, you get the same output, right? So you plug in something here and go here. If you go this way, you get the same result. I've got two statements that are both true. If the two vertical G2 and G4 are onto, and G5 at the end is 1-to-1, then the middle one is also onto. And the dual result of that is if these two are 1-to-1, G2 and G4 are 1-to-1, and the first one is onto, then the middle one is also 1-to-1. Pick either one of those and prove it. The proofs are very similar. But you only need to turn in one of them for credit. Number 2, this is called the 3x3 lemma, and you can probably guess why. Show if the columns are exact. So that means every map you see, the image is equal to the kernel at every stage. And we'll talk about that in a minute. If the columns and the top 2 rows are exact, then the bottom row is exact. I'm going to show you how to do this. I'm going to do the dual result. That is, if the columns in the bottom 2 rows are exact and the top row is exact, I'm going to do that one for you. Number 3, the snake lemma. This is actually very important in homological algebra. So if you have these 2 diagrams here, then there is an exact sequence from the kernel of this map to the kernel of this, and then this is called the connecting homomorphism, the snaky part, because you go from the kernel of this map, which is in here, to the co-kernel of G1, which is this modulo of the image. So you snake your way back over here and continue the exactness. So hopefully you'll get kind of a feeling for what exactness means. We're going to talk about this a little bit. It's called the snake lemma because you go kernel, and then you snake your way from A3 back over to B1 mod the image of G2. If you get, so let me say a word about homework as well. By the way, I do encourage you all to work together, right? You all are colleagues and all this kind of thing. I encourage you to talk about it together. I want you to write up what your thoughts are at the end of it. I know that there's this thing called the internet, and I'm not going to ask you not to use it, just use it with caution. Let me tell you how to cheat on this one. There's this movie from the 1970s called It's My Turn. Anybody ever seen this? It's kind of interesting. It's an awful movie. It really is. It's Jill Clayburgh maybe stars in it, and she's this professor who starts dating Michael Douglas, who's a baseball player. It's kind of a midlife crisis kind of movie from her point of view. And she's a math professor. And in the opening scene of the movie, she actually proves the snake lemma. Very hand-wavy, but if you're in trouble, you can always. But if you cheat by using the movie to learn how to prove the snake lemma, your punishment is you have to watch the entire movie. Number 4, an R module is said to be simple if the only submodules of S are itself and the 0 line. Show that any simple R module is cyclic, that is generated by a single element of this form here. And then characterize all R module homomorphisms from S to S, where S is a simple R module. Anyway, should be a little bit of fun. Diagram chasing is what you have to do with most of this, and I'm going to show you, hopefully you will agree, it is a fun little, whoops, It's a fun thing to do. Okay. So let's kind of move on. We will talk about exact sequences presently, but I do want to finish this up here. So if you remember, from last time, what we were talking about was how to characterize the direct sum sort of in a more concrete fashion. So let me briefly write this down. So you have AI. So you have AI, and this is a family of R submodules of A. Suppose that A is the sum. That is, everything in A can be written as a finite sum from some select ones of these. And two, we have this kind of, this is the directness part. For all K in the index set, if you look at AK intersect the sum, this is 0. If you have these two things going on, then A is the direct sum of AI. So let's prove this. So we'll define okay, so my input is going to be like some element of the direct sum of AI. So my output has to be something in A. And so you know what I'm gonna do? I'm gonna do something very naive. I'm just gonna do this. Now, first thing, perhaps this should make your spidey sense start tingling, or maybe something good. What's a possible hazard of this? Yeah.
If the sum could be diverged.
Right, I mean, this is not an 82 course, right? We're not sitting here trying to like prove that things converge, right? Nobody needs that. So I and I, this could be a very large index set, right? So, but this sum is actually finite because of the fact that this is the direct sum, right? So no problem. This makes good sense. These are our module homomorphism. This is easy to check. Just the way you add sequences, you add two finite sums and you get a finite sum, right? Everybody okay with that? So this is an R module homomorphism. So really what I wanted to show is this is one-to-one and onto. So suppose, let's say then this means now let's suppose that this is actually non-trivial in the following sense. There exists K and I such that AK is not 0. Right? So let's suppose this isn't just a sum of zeros. Suppose at least one of them has AK in particular is non-zero. This means that AK is equal to minus the sum do I agree with you? So this thing lies in AK because of that, and it's also in the sum of AI because of that. But by assumption, this is 0. So in other words, nothing in that sum can be non-zero, therefore. Kernel phi zero and phi is one. Is that okay so far? Yes.
So this is, we used to make this comment in maths class about this type of proof by contradiction. Would it have been okay to not make the assumption? We never used the assumption that AK is not zero. So is it okay to we just showed directly that AK
Yeah.
is zero? And
Yeah.
therefore-
I just kind of defaulted, right? I mean, so you probably got buddies in logic to get all mad about contradiction or something like that, right? Now, yes, you could certainly restructure it that way in this case. So how about on to? Well, let's suppose A. Right? Well, A is the sum of all those modules. So by the very definition of being a sum, that means that you can write this as each for some finite collection of indices in I. So we now define AI this xi this way by
Some of them, the
I'm sorry.
we don't define xi like the sum of all the injections of the above.
Well, actually, what I'm gonna do is something I think a little bit simpler. So I'm gonna let X.
Zero elsewhere.
And I'm gonna assume that these indices are distinct, so I don't confuse myself. And xi equals zero if I is not equal to I1, I2 up to I. And notice that by the definition, by the way we define this map, and so we get on to. Okay. Any questions on this? Okay, so I did promise that we were going to talk about exact sequences. So here we go. Exact sequences are important, very important in module theory. They're an important bit in homological algebra. Shows up, applications that show up in number theory, topology, all over the place. How many of you have heard of an exact sequence? Okay, so let me start off with a little bit of something more general. I'm going to add to this definition. One. A sequence of R model homomorphisms let's index this that way. Called a complex if, you might know what the definition of this is. A complex, if when you compose any two in a row, you get the zero. That is, when you do Fn. So when you do this twice, you get zero at any place, right? And this seems very kind of contrived, but there's many natural situations and applications of this where composing maps twice in a row gets you zero. These turn out to be quite important. Is exact at an. So we say it's exact at this one if the image of Fn is equal to the kernel of Fn plus 1. Notice this is a more specialized definition because for it to be a complex, what does this mean? It means when I go twice in a row, I get zero. So that means the image of Fn is contained in the kernel, right? When you get equality, you say it's exact at An, and the sequence is exact. If it is exact at An for all n. So I don't think any big surprises there, right? So sequence is exact here if the image of this is precisely equal to the kernel of this. And now I'm going to give you another kind of special type, and then I'm going to maybe give you some justification while we talk about this definition. An exact sequence of the form zero in the A, the B, and the C, zero, and we call this F and G, is called a short exact sequence. Let me make an observation or two. Okay, so the first natural question is who cares, right? So we've got these general exact sequences that could be infinitely long, right, in my definition. What's important about short exact sequences? Well, and why are they called short, right? Well, because if they're any shorter, they're boring, right? And I will give you an example of what I mean by that. And also, and this will be a homework problem play on the next set, it turns out that if I walk up to you on the street and give you any exact sequence, infinitely long even, you can make this exact sequence by splicing together appropriate short exact sequences. So in other words, short exact sequences are the atoms that build the molecules that are any exact sequence. So short exact sequences are the building blocks. So you can use those to weave together any exact sequence you want. And that's kind of a fun homework problem. Should we look at some examples here? Maybe a little bit of justification of why we talk about this in the first place. the sequence 0, A, B, F is exact if and only if F is. Anybody want to take a guess here? There's only one place for this to be exact at, right? Because there's only one module, namely A, that's got arrows going in and coming out, right? So what does it mean to be exact in what I've got there? F is 1 to 1. Because the image of this has to be 0, so that means the kernel of this has to be 0, so F is 1 to 1. Ooh, now I bet you can guess this. That's why they're dual notion. The sequence B, C, 0 is exact if and only if G is onto, right? Because the image of the kernel of this is clearly 0, right? Because there's nowhere else to go. So that means the image of this must be the kernel, so it's onto. And what about this? Because by the first one, H has to be 1 to 1, and by the second one, H has to be onto. H is an isomorphism. Yes,
Does that mean that both of those sequences are complexes no matter what you choose for F and G? Because
yeah, that's right, because, well, so, this one is, well, right, this one has to be a complex, a little baby complex, and this one does too, because there's only one place for hexagonals. And so, yeah. Oh, so you say it doesn't matter what you pick for X. Well, if you do this composition here, you get the 0 map, right? And if you do this composition here, you get the 0 map. So technically, yes. Here's another example. Suppose I have a homomorphism. Notice that I can build the following exact sequence. Well, so notice, so if I just give you any homomorphism in the world that I want, this is a short exact sequence, right? Because this is 1 to 1, because the kernel is a submodule of A, right? So this is a 1 to 1 map. And this is the projection from A into A mod the kernel of F, right? Which is clearly onto. And notice that the image of this kernel of F is actually the kernel of the next one. So I cheated, didn't I, a little bit to build that short exact sequence, right? Everybody okay with that? Here's one here. Here's sort of a practical one. This is one that's sort of a ripoff of this in a certain sense, right? This one's a short exact sequence where this first map is multiplication by n. So your input is some integer k. This goes to nk. And your second map is just projection on mod n, right? Notice that when you compose in the order, k to nk and nk mod n is 0, right? So it's exact, or so it's a complex here. And notice that the kernel of this, what must happen for this to be in the kernel is A must be a multiple of n, which puts it in the image of the previous one. So this is a short exact sequence as well. Okay. Let me give you another kind of good example. And this one is this one's sort of a short exact sequence on steroids a little bit. It's got a little bit more oomph to it. Whatever I'm up to F. So A. Let me tell you how this works. F and G. I want F of A to equal A comma 0. And I want G of AC, BC. Right? So A goes to the order pair AC and the order pair A0 and the order pair A prime C prime goes to C prime. This is a short exact sequence. Notice when you compose 2 in a row, you get 0. And also, if you look at the kernel of this map, the kernel of this map is precisely, you need 0 in the second coordinate. But if 0 is the second coordinate, it's in the image of this. Right. Everybody okay with that? This one is called, this one's called a split exact sequence. And we're going to talk more in depth about this, but here's kind of what makes this split. You can basically run this exact sequence in the opposite order, right? Notice there is an H here. There's this H from C to A sum C, such that when you do H, then you do G, it's the identity on C, right? And this H you need, well, what should it be? 0C. And there exists K from B sum, A sum C to A, such that when you do F and then you do K, you get the identity on A. And in this particular case, you will get K of the order pair AC to be A. So in other words, you could basically the sequence is reversible, right? In a certain sense, right? You can start here and do the exact sequence in the other order. Notice this one is not a split exact sequence. I guess technically, unless um, unless n equals zero, not zero, n is zero, that's not gonna be the, something 1 to 1, yeah. So I guess n equals 1, this would be an isomorphism, I guess. Notice that this is generally not a split exact sequence because you can't run this backwards here. If n is bigger than 1, because for example, if you have like z mod 2z, there's no 1-to-1 map from z mod 2z and z, right? Because z mod 2z is a torsion and z has no elements of finite order other than the identity. Yes,
Does that mean that the dual of an exact sequence is exact if and only if it's split?
what do you mean by the dual of the exact sequence?
When the arrow inverse.
Well, in general, so here's the problem, because when you have a short exact sequence, your problem is there may not be even a map at all that goes back here that makes any sense, other than the zero map, right? Because for example, if this is z to z mod 2z, the only map that you've got going backwards is the zero map, all right? So. Okay, yes,
Oh, so can you just remind us, because I think I've forgotten, but, and the answer might be no. But is this example of a split exact sequence supposed to be, like all encompassing? Like, are we supposed to think?
yes, we're gonna have a theorem about that coming out. Yeah. But in a certain sense, that's a very good question. It's because basically speaking, this is a little bit fast and loose, but basically speaking, if you have a split exact sequence, this is essentially what it looks like. Or it is isomorphic in some sense to a split exact sequence that looks like this, right? Let me point out that if you have a split exact sequence, and I'm going to go over this more carefully later, but if you have a split exact sequence, what's in the middle is the direct sum of the bookends, right? Which you notice in this case, it's usually not true, right? So this is usually not a split exact sequence, right? By the way, the converse isn't true. It is possible to have the middle be the direct sum of the bookends without the sequence itself being split exact, but it's not a trivial thing to construct such a thing. In fact, I believe that if the module is finitely generated, then split exact, if and only if. But once you have modules that are not finitely generated, you could run into a problem. Okay, so yes.
Do we still have a distinction between right and left split, or is it kind of removed by commutativity?
Yeah, that's another good question. I'm only thinking about commutative rings at this point, right? Yeah, so I don't want to delve into those woods. If you want to delve into those woods, come by my office and we'll drive each other crazy with it. So here's something that you saw from next homework. Consider the following commutative diagram of our module homomorphisms. With exact relation. So let's see. And one and two. F1, F2, F3, 4. G1, G2, G3, G4, 5, H1, H2, H3, H4. Okay, so what I mean is the rows are exact. The A1, B1, A5, B5 sort of don't count, right, because they don't have anything, but at every place where you've got a map going in and coming out, the image equals kernel. And the commutativity, that's what I said earlier, if you start anywhere, no matter how you take the road, you will get the same output, right? So if you start with A1 and go here and here, whatever you get is the same thing going here and here. And that works anywhere in there. Right. So if G2 and G4 are onto and G5 is 1 to 1, then G3 is on. So that's kind of cool because these two onto forces the middle one to be onto if you've got 1 to 1-ness here, right? And that's kind of weird, right? And it shows kind of the intimate relation between 1 to 1 and onto, which isn't completely clear when you first define 1 to 1 and onto. And here's the dual result. If G2 and G4 are 1 to 1 and G5 is onto, then G3 is 1 to 1. So these two 1 to 1 and not G5, G1. If G1 is onto, then the middle one has to be 1 to 1. So that's a homework exercise. Here's a corollary to this, and I will actually directly prove the corollary, which, and the reason for this is maybe it will give you kind of a leg up on knowing how to do these so-called diagram cases. Corollary. Consider the commutative diagram of R module homomorphisms with exact rows. Very much like the previous, I think. Okay. So here's the conclusion of the theorem. If G1 and G3 are onto, so if G2, if G1, G3 are 1 to 1, so it is G2, and 3 if G1, G3 are isomorphisms, so is G2. This, by the way, is called the 5 lemma. I bet you can guess why. And this one is called the short file lemma. Notice, let me make a couple of remarks before I get rolling here. Notice, it's clear, isn't it, that 3 follows from 1 and 2, right? Because isomorphism means both 1 to 1 and on to. Notice that this follows directly from the 5 lemma, right? It's an easy corollary to the 5 lemma, because in the short 5 lemma, these animals at the end are zeros. So the extra bit that you need, that it's G5 is 1 to 1, or G1 is onto, are trivially satisfied because you have only, basically it's the identity morphism on the 0 module, right? So in a very silly way, those extra conditions are satisfied. Everybody okay with that? But of course, we haven't proved 5 lemma. So let's do the short 5 directly. This method of proof is almost more fun than you can legally have with some colored chalk. So yeah, I'm actually kind of grateful I'm recording this so you all can, you don't have to write too much stuff, because this is a lot of fun to do, but you'll probably see pretty quickly why it's a little bit obnoxious. It's not terrible if you're organized about it, but it's a little bit obnoxious to write down details to it. Okay. So what do I want to do here? I want to show that if G1 and G3, G1 and G3 are onto, so is G2. So suppose G1 and G3 are onto. So I want to prove that this G2 is onto. So let's let B2 be in B2. I've got to find something that goes here, correct? So what can I do? Start breaking out the colors. Keeping white's acceptable today. So if there was something coming from here, it'd be good to go. But you know what I'm gonna do? I'm gonna push this on here. B3. So B3 is actually, when I do this kind of arrow, this is H2 B2, right? Now, what do I know about this map here? It's onto, right? So I don't know much, but I know that up here there was some A3 that goes to B3. Now, what do I know about F2? Well, that top row is exact, short exact, right? And so what does it mean for a sequence to be short exact? Well, the last map must be onto, the first map must be 1 to 1, and the middle one is kernel image thing going on, right? But in particular, this last map is onto, right? So there's an A2 that goes here. Oh, I'm just dying for that A2 to go down to B2. But I don't really know that that's the case, right? So I can push A2 down here to something else in B2 called X, all right? So let me kind of write that detail here. G2 of A2 equal X. Well, I didn't necessarily get to B2 because nobody said that X and B2 had to be the same thing. Oh dear, whatever will I do? Okay, so the diagram's commuted, so what does that give me?
So you know that H2 of X is, we already found H2 of X.
Right. Going here gets me B3. So going this way must give me B3. So that means that by the commutativity of the diagram, H2 of X must also be B3. So B2 and X both go to the same thing. How does that help? Let me ask you this. So what we have is I have what? G2, B3 is H2 B2, and it's also H2 of X. Right? So let me ask you this, what is H2 of B2 minus X? It's 0. So that is this is in the kernel of H2. But what is the kernel of H2 equal to? The image variable. So here, right, so I've got this animal here, we'll call it B1, that goes to B2 minus X over here, right? Well, let's continue the chase because guess what? This one's on to you as well, right? So there's an A1 that goes here. Now, so this goes over here somewhere, not necessarily A2, but it goes over to some Y here. And where does Y have to go? That has to go to B2 minus X, right? So by that part of the chase here, G2 of Y has to go to B2 minus X. Can anybody finish the thought for me? Let's look at G2. Y plus A2. Right, because Y plus A2 is known as A2, right? What happens when we do this? This is G2 of Y plus G2 of A2. And what is G2 of Y? And
X.
so G2 of something. Now tell me that's not sexy, right? I mean, that is really awesome, right? I mean, that's really cool. So, I think that's probably a good place to start. Put that in your pipe and smoke it, and we'll look at the other one, the dual result next time, and move on with this. Any questions? All right, math club today, it might be elementary for some of you, but there might be a few little nuggets that you haven't seen before. I'm gonna talk a little bit about power series and what you can do with them. Other than that, y'all have a good weekend, and I will see you on Monday. Oh, yes.
What's the go kernel exactly? What's the go kernel exactly?
Oh, right.
Yes.
Let me remind you.
I read about this one.
If you have a homomorphism,
Where you suppose which is never used. So the line of reasoning here, suppose AK is not zero. We showed directly that it is zero, which contradicts that it's not zero, and therefore it is zero. That's like a that.
that's
Okay, not zero. We showed directly